And then there's some writing dissociation reactions and calculating pHs based upon concentrations for a couple other acids and bases. And then there's a lab, um, and your job in the lab is to figure out what the approximate pH is with different concentrations of different unknowns, and those unknowns are on the lab tables. So anyway, uh, there's some things to know all the time about relating pH, hydroxide, or pH, hydrogen, hydroxide. What's up, Charlie? Yeah. You know where they are? All right. So things that are true, pH plus POH is always equal to 14. Um, and then other things is that a pH is equal to the negative log of the hydrogen concentration. POH is equal to the negative log of the hydroxide concentration. And then you can get from hydroxide concentration, or from pH to hydroxide concentration and hydrogen concentration like this. Hydrogen concentration is equal to 10 to the negative of whatever the pH value is. And also the hydroxide concentration is equal to 10 to the negative POH. So generally we talk about pH because it's the most common way to talk about whether stuff's acids or bases, but there's also this factor called POH, which is the inverse log of the concentration of the hydroxide amount too. Let's see, desktop 2, that's on, right? Share. Okay. So some things you could fill in real quick and real easy is if you know a pH value or a POH value, you can just subtract them from 14. So the first thing I can look at is, well, if pH plus POH is equal to 14, we did this one yesterday, but if you take 14 minus 3.78, you get 10.22. Or if you take 14 minus 8.46, you get 5.54. And up here, if you got a POH of 5.19, that's associated with a pH of 8.81. So all the time, the pH plus the POH has to equal 14. So those are the things you can fill in really easily. And then if you want to calculate a hydrogen concentration from a pH, it's always just 10 to the negative pH. But here's the thing, you don't write it as 10 to the negative 3.78. It's not acceptable in scientific notation to have exponents that are not integers. So you want to evaluate what that is. On your calculator, you can just hit like 10 caret negative 3.78. And watch out, because on the right-hand side, there'll always be times 10 to the something. And this is 1.66 times 10 to the negative fourth. Same thing over here for POH. The POH is the hydroxide concentration is equal to 10 to the negative POH. So whatever 10 to the negative 10.22 is, that's like 6.03 times 10 to the negative 11th. And then we'll do the acid or base thing later, but usually the easiest way to figure out if it's an acid or base is based upon the pH. So that's that one. For here, for 8.81, this comes out to be 1.55 times 10 to the negative 9th. And for 8.46, it's 3.47 times 10 to the negative 9th. And again, to go from POH to hydroxide concentration, you just take 10 to the negative or whatever this is. So 6.46 times 10 to the negative 8 or 6th. And this is, let's see, 2.88 times 10 to the negative 6th. These are all in concentrations and molarity. And then you got these ones where you know the hydroxide concentration. So, or the hydrogen ion concentration. So if you have the hydrogen ion concentration and you want to find the pH, it's just equal to negative log of whatever the hydroxide concentration is. So on your calculator, if you just hit negative log and then 3.89 times 10 to the negative fourth. Oh, that's weird. Let's see. This calculator doesn't do the parentheses. There we go. So it's like 3.41. Same thing down here. Negative log of whatever this value is 12.1. And then because you have pH values, you can then fill out the POH. So subtracting 14 from subtracting 3.41 from 14 gets you 10.59. Subtracting 12.1 from 14 is 1.90. And then you could do the same thing to go from pH to OH, just like I did up in this one. You take 10 to the negative pH power. This comes out to be 2.57 times 10 to the negative 11th. This is 1.26 times 10 to the negative 2. This one here is the only one that's, kind of on its own. With a hydroxide concentration, you could figure out a pOH by just going, the pOH is equal to the negative log of whatever the hydroxide concentration was. And that comes out to be 5.31. And if the pOH is 5.31, you can subtract that from 14 to get the pH, 8.69. And then take 10 to the negative 8.69, and you get 2.04 times 10 to the negative 9th. So all these relationships go that the pH plus the pOH, these add to be 14. The sum of the pH and pOH is 14. Another thing that's true is that the product of the hydrogen concentration and the hydroxide concentration is always equal to 1 times 10 to the negative 14th. In other words, the hydrogen concentration times the hydroxide concentration is always 1 times 10 to the negative 14th. If you take 1.66 times 10 to the negative 4th times 6.03 times 10 to the negative 11th, you're going to get 1 times 10 to the negative 14th. And then whether they're acid or base just depends upon the relative pH. So the first two are acids, and then the last four, these are all bases. So base. That's the plan. I'll leave this up whenever we do in the lab to help you out with getting between the values. But these are the relationships between all the different ways to get around relating pH, pOH, hydrogen, and hydroxide concentrations. Another thing that I mentioned that you might see is that the hydrogen concentration is always the same as hydronium concentration. And that's because in water, what happens is these hydrogen ions actually get together with waters to make this ion called hydronium. So hydrogen ions don't actually chill out in the water on their own. They always get together with the water and make hydronium. So it's also true that sometimes these references will be not for hydrogen, but for hydronium. Those will be exactly the same values. Okay, so let's see. I did the one yesterday, I guess, for sulfuric acid. Let me go back and check. I think so. See if this was from yesterday. Must have been a different one. Anyway, we did the first one with the sulfuric acid yesterday. The number 3 says write the equation for the dissociation of sodium hydroxide. So you should be able to write the equation for sodium hydroxide. On the periodic table, sodium is a group 1 element with a charge of 1 plus, and hydroxide is on the anion chart and has a charge of 1 minus. So sodium hydroxide is made up of sodium and hydroxide. The dissociation reaction is actually just the reverse of how you'd write the equation. You've got sodium hydroxide dissociates into sodium and hydroxide. Why that's important is in this equation, the ratio is 1 to 1 to 1. There's 1 sodium hydroxide, 1 sodium, 1 hydroxide. So if the concentration of sodium hydroxide, instead of writing out the words the concentration of, you just put it in a bracket. So putting NaOH in a bracket means the concentration of sodium hydroxide is 0.00841 mole. I need another 0.000841 molar. The concentration of hydroxide is exactly the same. The time it's different is if the ratio is not 1-to-1. In other words, like if there's 2 or more hydroxides. So what we're trying to figure out is what's the pH. If that's the concentration of hydroxide ions, we got to get the pH. So the smart thing to do is with hydroxide concentration, figure out what the pOH is. And the pOH is equal to the negative log of the hydroxide concentration. So if I take negative log of 0.000841 molar, let's see, negative log 0.000841, it's 3.08. And if the pOH is 3.08, because pH plus pOH is always equal to 14, if I just take 14 minus 3.08, that gets me what the pH is. And it's, I guess, 10.92. We really only have 3 significant figures, so like 10.9, but it could be 10.92. And there's not really a unit for pH. So a smart thing to write is the pH is equal to 10.9. It makes sense to be greater than 7 because sodium hydroxide is a base. You expect the pH to be bigger than 7, and the pH is greater than 7. So if you do a problem about like what's the pH of something and it's an acid, you should expect a value less than 7. If it's trying to figure out the pH of a base, you should expect a pH that's greater than 7. All right, so then there's 2 other ones. We want to look at what's the dissociation of calcium hydroxide. In that one, because there are 2 hydroxide ions for every calcium ion, calcium hydroxide dissociates into 1 calcium and 2 hydroxides. So whatever the concentration of calcium hydroxide is, the concentration of the hydroxide by itself is actually twice as great. And this problem, has you synthesize some stuff that you already know earlier in the course. We've got 2.55 moles of calcium hydroxide in 10.2 liters of solution. With that, we can figure out the molarity. The molarity is the number of moles divided by the volume. So if I take the 2.55 moles of calcium hydroxide and divide that by 10.2 liters, that'll tell me what the molarity of the calcium hydroxide solution is. 0.25 molar. But that is the concentration of calcium hydroxide. In the reaction, for the dissociation, for every 1 calcium hydroxide, there are 2 hydroxides. So what you can write is, because the 0.25 molar is the concentration of calcium hydroxide, you can use a mole ratio that in this dissociation reaction, for every 1 calcium hydroxide, CaOH2, you get 2 hydroxides. So then that'll be 0.50 molar is the concentration of hydroxide. That's what you use to be able to figure out the pH. So if you know the concentration of hydroxide, you can calculate the pOH, which is equal to the negative log of the hydroxide concentration. Let's see, negative log of 0.5, 0.30, let's see, 3 significant figures. So 0.301, that's the pOH. The pH is then equal to 14 minus whatever the pOH is. 14 minus 0.30 is 0.301. 13.7 is the pH. It's a fairly high pH. It's pretty close to 14. So, and then number 15, I'll just do this real quick. You got a mass of HBr. as an acid is hydrobromic acid. So we got 40.5 grams of HBr dissolved in 1,500 milliliters of water. We need to get to a concentration. So the first thing is this 40.5 grams, you can convert that into moles. The formula mass for HBr is 81 grams per mole. So that comes out to be a half a mole. And we've dissolved half a mole in 1,500 milliliters of water. So the molarity is half a mole in 1.50 liters. 1,500 milliliters is 1.5 liters. 0.5 or 1.5. Oh yeah, or 1/3. 0.333 molar. Because hydrobromic acid, HBr, for every one HBr, there's one hydrogen. This is the concentration of both HBr and it's the concentration of the hydrogen ion. Because there's only going to be one hydrogen for every HBr that you end up with. So that's the concentration of hydrogen ions. The pH is just simply the negative log of whatever that hydrogen concentration is. 0.333 molar. I don't know what that comes out to be. Negative log 0.333. Like 0.477. pH is about 0.4. So pH can be a value that's, it doesn't have to be from 1 to 14. pHs can have values less than 7 for acids and any value greater than 7 for a base. All right, so the lab, at each of the tables, there are dropper bottles. Those dropper bottles have solutions in them. They're clear and colorless, but it's not just water, they're acid or base solutions. There's also some pH paper. It's a different pH paper than what you use in the other acid and base lab. It's a universal pH paper, so it can change to many colors, and you'll see there's a color guide in and with the box. There's also a well plate. The well plate is just a little plate that's got some holes in it. So it's just like a plastic plate. We used them earlier. There's a bunch of holes. You don't need a whole bunch of holes. Like you only just need a couple of them. But what you want to do is put a little bit of sample in the bottom of a well plate hole. So you got the well plate hole, get a little bit of your sample down in the bottom, and then you can dip the paper into it. You never want to put the paper into the sample of the thing that you're testing because you contaminate whatever you test. Instead, you dispense just a little bit with an eyedropper, with the dropper bottle, into a well plate, and then you test in there, and then that gets disposed of. So there's these different unknowns, unknown 1, unknown 2, unknown 3. You test the color of the paper, and from the color of the paper, you tell the approximate pH. And the 3 different unknowns are either 100th molar sulfuric acid, or 1,000th molar hydrochloric acid, or 100th molar sodium hydroxide. And based upon those concentrations of sodium hydroxide, you can calculate the pH and identify which of the unknowns it was. Or on the back, 100th molar hydrochloric acid, what would the pH of that be? And does that match one of the unknowns? The unknowns are fresh, they're newly made up. It should work out just right. Because we're working with acids and bases, especially important with the bases, you got to wear goggles. So I'll get the goggles down. I'll put those on the middle lab table. The best thing for you to do, I'll put this one back up. These are the solutions for the first page. And then if you're remote, in the folder for this week, let's see. The lab says identifying unknown acid and base activity. Whenever you click on that, the lab is, oops, I can't believe I just hit the power button on there. Anyway, the lab is down here toward the bottom, but there's a color guide for universal indicator paper from pH from 1 to 7 and then 8 to 14. And then these are the samples that students are using, unknown 1, unknown 2, and unknown 3, and the way the paper turns out as a result of the test. So that's how you can see the data, is how that goes. Let me see. All right, I guess that's what I got to tell you about. So get the goggles out. Make sure your goggles is and then all the waste that goes in the down the sink, it's all safe to go down the sink as well as to the sewer. All right, remote stop recording.